Good morning. We will now begin this morning's program. First, thanks to the Wisconsin Center and the staff for their excellent service this morning. As you can tell, I do my shopping at the same place as the wait staff. Mattock appreciates the support we continue to receive from the publishing community. Two publishers have shown their exceptional support by becoming Mattock corporate sponsors. We will begin the program this morning with a message from representatives from our corporate sponsors. First is Hawks Learning Systems, represented here by Marcel Prevuznek, the Vice President of Product Development. Marcel is also an adjunct professor of mathematics at Trident Tech in Charleston. He's teaching a hybrid stats course right now.
Thanks, folks. Thanks, Jim. And I hope everyone's had a chance to get some coffee and some food and had a good breakfast. My name is Marcel Prevuznek. I'm Vice President of Research and Development for Hawks Learning, and I am an adjunct instructor of math at a technical college in the Charleston, South Carolina area. This year, Hawks is celebrating its 40th anniversary. And as a company that was founded and operated by math instructors and statistics instructors, we have a mission to create opportunity through deeper level learning. And I think when I was talking to some folks last night, they mentioned they learned some stuff here during this conference. I think pretty much everyone would have that as a takeaway. You've learned something that you're going to take back to your institutions, back to your faculty, and most importantly, take back to your students. So definitely we appreciate the opportunity to partner with the Mattock organization to help deliver this professional development that you will hopefully benefit from. And if you haven't learned anything yet, you still got about a day left, so make the most of it. I would like to also thank, on behalf of Hawks, the executive board, the conference committee, the local committee. Y'all have done a great job putting this together, and please join me in giving them a round of applause. Thank you very much, and I look forward to seeing you guys next year in Spokane.
Our second corporate sponsor is Mcgraw-Hill Education, and I'd like to introduce their representative, Mary Ellen Ron, Executive Marketing Manager for Alex. Mcgraw-Hill sponsored John Urschel to attend this year's conference. Many of us saw John's wonderful presentation yesterday morning.
Good morning, good morning. I think this is my 9th Mattock, and I just wanted to say how much we enjoy it and look forward to it every year at Mcgraw-Hill. And on behalf of Mcgraw-Hill, I'd like to thank you all for our continued partnership with the Mattock organization. We were so happy to join you here in Milwaukee and take part of all the timely conversations, but specifically equity. We were inspired by John Urschel yesterday, and we hope all of you were as well, as he reminded us that equity in education affects everyone. And at Mcgraw-Hill, we want to partner with you on this journey to drive systemic change. We acknowledge that every student has unique backgrounds, and we know that students all start in different places, but with modern and adaptive technology like Alex, they have the opportunity to all finish in the same place. Our tools can help you reach your students and intervene before it's too late. And we look forward to partnering and supporting you with our resources and partnering with you on your journey as you continue to support all students. We look forward to continuing this partnership and continuing the conversation as we reach out and work with you, and look forward to seeing you in Spokane.
It is our tradition here at Mattock to recognize our volunteer leaders on Saturday morning. All of these positions have term limits, so we are always seeking new members to step up when our leaders complete their terms of service. It is my pleasure now to introduce to you the 2018-2019 Executive Board for Mattock. While I believe each of these individuals mentioned here today deserve a round of applause, please hold your applause until all of the introductions have been made. Kate Kozak, President-elect. Jane Tanner, past President. David Tanner, Treasurer. Behnaz Rouhani, Secretary. Sophia Georgiakaki, Northeast Vice President. Dan Faringer, Mid-Atlantic Vice President. Nancy Rivers, Southeast Vice President. John Oakes, Midwest Vice President. Rochelle Beatty, Central Vice President. April Strom, Southwest Vice President. Sarah Pauley, Northwest Vice President. And Eric Matsuoka, West Vice President. Mattock's Executive Director is Ann Dudley. The Mattock office staff include Beverly Vance, Office Director. Christine Schott, Publications Director. Christy Hunsucker, Accounting Director. These colleagues are responsible for the day-to-day operations of the organization. Collectively, they have over 60 years of experience. To the board and staff, thanks for all you do. Mattock has 45 state, provincial, or regional affiliates. Will all the affiliate presidents in attendance please stand and be recognized? Thank you. We have several past Mattock presidents registered for the conference this year. Carl Smith, Jim Rosnowski, Phil Mailer, Julie Ackerman, Nancy Sattler, all up here in the front. Would the Mattock past presidents please rise and be recognized? I thank you for your continued service to the organization. Continuing our leadership recognition is the conference committee. These colleagues work throughout the year to bring us a wonderful conference. The conference committee is led by Kevin Doctor, conference coordinator. Kevin is retiring after his 11th year as conference coordinator. Natalie Vega Rhodes, assistant conference coordinator. Judy Williams is the program coordinator, and Tim Britt, assistant program coordinator. Judy and Tim were assisted this year by program committee members Michael Pemberton, Beth Tsai, Damian Adams, Kim Granger, and Julie Phelps. The academic committee chairs and ANET leaders also serve on the program committee. Together, the committee puts together our wonderful conference program. Continuing with the conference team members, Crystal Wiggins, advertising chair, Todd Stein, exhibits chair, and Sarah Miller, roommate network director. Thank you, conference committee. I'd like to call Turi Suski to the stage. About 4 years ago, I attended a Wismatic, right here in the state, meeting. I asked for names of anyone interested in becoming the 2019 local events coordinator for Milwaukee during a business meeting. And as soon as I posed the question, all eyes went to Turi. I knew then that we had a winner. For over 3 years, Turi's been working with the local committee, which is not so local, pulling in from 3 surrounding states and 1 rep from Florida. They do so many things: create the conference logo, identify 2 wonderful speakers, Alan Zolman and Michael Steele, write numerous articles for the AMATIC newsletter, help with logistics and the signing of the conference, set up and schedule members to work at the Palm hospitality area, promote this conference at previous conferences and affiliate conferences, and finally summarize the previous year's conference evaluations. This, of course, just touches the surface of all that they do. Members of the local committee, will you please stand and be recognized? Please continue standing. Turi, on behalf of AMATIC, I'd like to thank you for all your work at as the 2019 Local Events Coordinator, and I'd like to present to you this plaque of appreciation.
Thank you.
Continuing our leader recognition are the academic committee chairs, ANET leaders, and subcommittee chairs. Again, please hold your applause till all have been introduced. Paula Wilhite, Developmental Mathematics Committee Chair. Dan Mattock, Innovative Teaching and Learning. Dorota Zak, Equity Committee. Stefan Brado, Math and its Applications for Careers. Bob Capetta, Math Intensive. Rachel Bates, Placement and Assessment. Ann Sittimer, Research in Mathematics Education for two-year colleges. Julie Hansen, Statistics. Mark Coleman, Teacher Preparation. Helen Byrne, Pathways Joint Subcommittee. And Bika Silva, Data Science Subcommittee. Our impact leaders, Julie Phelps, Mathematics Standards in the first 2 years of college. Evan Evans, the Digital Products Coordinator, Impact Live. And our ANET, AMATIC Network, or ANET leaders. Christine Mirbaha, Division Department Leadership. Steve Kravisky, International Mathematics. Judy King, Adjunct Faculty Issues. And Ferry Sami, Math for Liberal Arts. Thank you, committee chairs, subcommittee chairs, and ANET leaders. The Student Math League is led by coordinator Steve Hundert and test developer TJ Duda. Steve Blasberg is the Faculty Math League coordinator. Would Steve and is Andrew Noble here? No, Andrew? And our awardees, please join me on the stage. Are they here?
I think they're here. It's Roger Wolf.
Roger Wolf, team?
So last year's AMATIC Student Math League competition involved over 12,000 students at 157 schools, and it takes a big team to make this run. So I want to thank Pearson Education for generously funding our grand prize, a $3,000 scholarship, Mu Alpha Theta for providing copies of Mathematica to our top 10 players, and the Association for Women in Math for providing membership to our top women. I also need to thank TJ Duda and the Test Development Committee for providing the test questions, and just as importantly, the answers for the competition. George Hilbert for maintaining the website and electronic scoreboard, Randy Schwartz for supplying the solutions you find on the website, and Beverly Vance and Christine Schott in the AMATIC office for too many things to mention. And of course, a big thank you to all the moderators and other faculty who recruit our players, run practice sessions, administer the tests, grade the tests, and post the scores. This league would not exist without everyone's efforts. The 2018-2019 top team in the nation is Los Angeles City College and winner of the Glenn Smith Team Award. This year, this award is a little bit bittersweet. Longtime moderator and coach of the team, Anatoly Nikolic, died unexpectedly last summer. Won't be here to accept the award. But in his place, we have the new moderator, Roger Wolf, along with some of the team members, Anna Alberdian, Miriam Alberdian, and Mikita Dimitrov. Congratulations. All right, enough with the kid stuff, and on to the pros, which of course means the Steve Blasberg Faculty Math League, where once again the much coveted regional plexiglass trophy is up for grabs, as well as both bragging rights and a cash prize generously funded by Mu Alpha Theta for the top individual. And here to present the award is Steve Blasberg.
So the top three individuals for this year's Faculty Math Week competition, number 3 is Sean Sanders from Sheridan College in Ontario. Second place, a longtime competitor for us, Curtis Mitchell from Kirkwood Community College in Iowa. And this year's Faculty Math League winner, also a longtime competitor for us, is Aisha Arroyo from Middlesex Community College in Massachusetts. You may have noticed that 2 of those 3 competitors are from the Northeast, which also took 6th place, and as a result, the winner of this year's regional competition and the new owners of the much fought for trophy is the Northeast.
Thank you, Steve and Steve. Pearson sponsors the Charles D. Miller Scholarship Individual Student Award. We are checking eligibility, but we are pretty sure that the winner is a student on this list. We will announce the individual winner as soon as eligibility can be confirmed. Pearson also sponsors the AMATIC Teaching Excellence Award. We thank Pearson for their support. The other student math competition in AMATIC is the Student Research League. Leaders include Karen Gaines, the Student Research League Coordinator, Holly Ashton, the Thesis Defense Coordinator, John Pazdar, Development Coordinator, and Pat Hershey, Overall Competition Evaluator. Would Karen and student awardees and mentors please join me on the stage? This year marks the 2nd year of the Student Research League student competition, modeled after SIAM's Moody's Math Challenge, now MathWorks Math Modeling Challenge. This competition for students in the first 2 years of college challenges student teams to use mathematical modeling to answer open-ended questions, such as what is the safest place to live in the US, or what is the best sources of energy to use at a randomly selected home in your city. Please consider mentoring a team of 1 or 2 or 3 students at your college. Registration begins January 1st. Our 3rd place team is the team of Rebecca Rosenblum, Richard McGarry, and Colin Devine from Holyoke College in New York. Rebecca and Colin are here to receive their awards. Their mentor is Ileana Vasu. The team members will receive a plaque and a scholarship for $500 each. Congratulations, Rebecca and Colin. Our first place team is an individual. Ashley Lesher attends Hopkinsville Community College in Kentucky, and her mentor is Arthur Schultz. Ashley will receive a plaque and a scholarship for $3,000. Congratulations, Ashley. Thank you, Karen, and congratulations, student math modelers. Other members who fulfill important AMATIC leadership roles include Peter Georgakis, legal advisor, Wendy Morrison, editing director, Rita Ralph, Mu Alpha Theta liaison. We have several members working on and writing grants. Dennis Ebersol is the grants coordinator. Megan Bright Goodwin is leading Project Slope. Laura Watkins is serving as liaison to at least 3 other grants that have received NSF funding. Leaders of AMATIC's publications include Jennifer Travis, AMATIC News Editor, George Hurlbert, Website Coordinator. Joanna Debrecht is a Journal Editor, George Alexander, Journal Assistant Editor, and Wendy Morrison again, the Journal Production Manager. Pat Riley is Webinar Coordinator, Mary Menard, Traveling Workshop Coordinator. In addition to AMATIC board members and the Executive Director, who serve on the Foundation Board, 4 individuals round out the Foundation Board. They are Fred Peskoff, Ernie Danforth, Cheryl Cleaves, and Bill Stinken. Christy Heidegger coordinates AMATIC Project Access. You see the current cohort there. Will all of the AMATIC Project Access Fellows and the Project Slope Fellows, please, both past and present, please stand. Many future leaders of the organization. This concludes the leader recognition. I'd like to thank all 120-ish AMATIC members who have served on committees in some other leadership role over the last year. The last presentations, 2 presentations, before our keynote speaker is the presentation of the Herb Grouse Presidential Awards. Will John Pasdar and Karen Gaines please join me on the stage? The Herb Grouse Presidential Award is an award recognizing exceptional service to AMATIC and to our profession. First, Karen. Karen began her career as an electrical engineer in 1986 with McDonnell Douglas. But after 4 years of working in industry, she heard her calling for education, earned a master's degree, and began her teaching career at the community college. She has worked at her current college, St. Louis Community College, Merrimack, for 23 years and counting. Throughout her career, Karen has been an advocate for STEM education. For example, she collaborated with her STEM colleagues at St. Louis CC to develop interdisciplinary activities in physics, in anthropology, and in other science disciplines. Also at St. Louis CC, Karen created a math course for her students on crime solving and forensic science. She's been recognized by her college and her colleagues with statewide and national awards for excellence. Throughout her teaching career, Karen has been involved in grants, both leading grants and participating in grants. She created classroom resources on 2 NASA AMATIC collaborative grants in the late 1990s, an NSF-funded grant named Dimensions Program in 2009, and played a leadership role in an NSF-funded MathWorks grant. Karen has shared her talents with her AMATIC colleagues. She was involved in the support and development of Project Access, and became AMATIC's first Project Access coordinator after the initial Access grant from ExxonMobil expired. She served in that position for 5 years. She continues to serve as a mentor for new Access Fellows and has donated generously over the years to support the program. Karen's service to AMATIC continued in 2016 when she became involved in AMATIC Impact, one of AMATIC's signature publications. Karen was on the project steering committee, served as a chapter writer on ownership, and served as a principal editor for the entire document. And here's a newsflash. Karen and a team of AMATIC members, after 2 years of work, have drafted a $3 million grant proposal named Teaching for Prowess that will be submitted next month. We'll keep our fingers crossed. In 2017, Karen helped create the AMATIC Student Research League, AMATIC's second math competition. Karen was the first coordinator of the Student Research League and continues to serve in that position, overseeing all aspects of the competition. Currently, Karen is a leader of Impact Live, the companion member website to AMATIC Impact, my.amatic.org. She is on the website design team and is instrumental in setting the guidelines for the discussion boards, content, and other features of the site. In 2018, Karen became a member of an AMATIC team developing curricular resources for an emerging AMATIC initiative, AMATIC's Journey to Mars. Each of these curricular modules will demonstrate the mathematics involved in NASA's current space exploration initiatives. Soon these modules will be available to all faculty teaching mathematics in the first 2 years of college. Karen has provided and continues to provide exceptional service and leadership to her college, her colleagues, and to AMATIC. Thank you, Karen. I present to you the AMATIC Herb Grouse Presidential Award.
Pushes me around all the time.
Our second awardee is John Dyer. AMATIC, the organization, began in about 1994. John was there. He's a charter member of the organization. He's also a charter member of the affiliate Mattock. John began his teaching career as a high school teacher in 1964 and began teaching at the community college in 1967. John taught at Capital Community College in Connecticut for about 35 years, and for several of those years served as department chair. After retiring in 2002, he continued to teach part-time until 2011. One of John's innovations at Capital was the creation and production of a basic algebra course for television in 1977 and 1978. He was a pioneer for distance education in the early years. John's service to his profession includes significant work beyond the work at his college. He was AMATIC's grants coordinator from 94 to 99, and then again from 2013 to 2016. He has given numerous conference presentations related to his work on grants. In addition to helping others write grants, he has collaborated with others on several AMATIC grants. For example, John led a grant team from the ExxonMobil Education Foundation called a National Center for Developmental Mathematics for two-year colleges in 1988 through 1994. In the late 90s, John led 3 NSF grants that created a collaboration with NASA. A blurb in the AMATIC history document describes these grants. It says, AMATIC endorsed 2 NSF grants written by John Dyer and colleagues, where AMATIC members were selected in the summers of 1996 through 2000 to develop 20 mathematics modules and 40 spin-off activities for two-year colleges at NASA's Kennedy Space Center, Florida. From these AMATIC grants, 2 books were published showcasing the classroom resources of the grant participants. From 2001 to 2003, John led an NSF grant titled The Math Works. Like the previous grants, this grant led to the publication of the book Mathematical Journeys 1, another resource for college math professors. And from 2009 to 2011, John led an NSF grant called the Dimensions Program. Like other grants, this grant led to the publication of the book titled Mathematical Voyage, the Dimensions Program. In these AMATIC endorsed and administered grants, the proposal reviewers, grant writers, and project evaluators were all AMATIC members. For his leadership, the grant participants in the early days affectionately named him the Grand Poobah, and still call him that till this day. More recently, John became involved in some non-grant activities. He envisioned and created the new AMATIC Student Research League in 2017, where he served as the competition's development coordinator. We will begin the third year of that competition in 2020. Currently, John, as project leader, has once again assembled a group of AMATIC members, as he has so many times in the past, to write modules for the new program, AMATIC's Journey to Mars, a proposed collaboration with NASA. When I shared with John what I was going to say about him today, he identified one glaring omission. He wrote, "There is a saying that behind every successful man is a woman," and he wanted to thank Dr. Patricia Hershey for her guidance in keeping him focused over the decades on all of these grant proposals and not letting him wander off on far-out schemes and ideas. Thank you, Pat. Pat is also a 4 decades member of AMATIC. John has provided exceptional leadership to his colleagues, his students, his college, the research community, and AMATIC over his long and distinguished career. Thank you, John. I present to you the Herb Grouse Presidential Award. And now to our keynote. Our breakfast this morning is Dr. James Tanton. James is a Princeton-educated mathematician. He is an ambassador for the Mathematical Association of America in Washington, D.C., currently serving as their mathematician at large. He is an author. His writings include the books Solve This, Math Activities for Students and Clubs, and Mathematics Galore. He has a large presence online through his many resource websites and YouTube videos. James is a teacher. He worked as a full-time high school teacher for 8 years in 2004 to 2012. While at the high school, he helped students pursue research projects and publish their results through an extracurricular program that he created. He is a teacher educator. He teaches mathematics courses and conducts workshops for mathematics teachers. He creates video courses, advises on curriculum, and gives demonstration classes and lectures across the nation and around the globe. James also leads the Mathematical Association of America's Curriculum Inspirations Project. He serves as a chair of the Advisory Council for the National Museum of Mathematics, and is the founder of the Global Math Project, an initiative to transform the entire world's perception of what mathematics can and should be. From his Twitter account, James is described as an Aussie fellow promoting uplifting, joyful, genuine math thinking and doing for students and teachers alike. Please join me in welcoming Dr. James Tanton as he gives us several proofs of 2 equals 1.
Thank you, mate. It's wonderful. All right. Do I have a mic? No, we don't have a mic. All right. Okay, I walk around a lot, so I'm not going to be able to stand here. So let's see how we do this. So, lapel mic. All right, before I begin, though, while we're fussing around, I need to check one very important thing. Is AMATIC aware that there's an international mathematics salute? No. All right, would you like to learn the International Math Salute? The answer is yes, by the way. Okay, yes, okay. Watch out, it is strange and weird and goes as follows. So you need to put everything down. Coffee mugs down, breakfast down, because you need your arms completely free for this. All right, goes as follows. arms out front. Great. Right hand over left hand. That's the hard part. Got that? All right. Then you go palm to palm, and then the salute gets weird. You wiggle your little fingers. Then you wiggle your thumbs. Then you wiggle your little fingers again. And then when you're ready, just come on back. Are you mad at it? Whoa! All right, amuse yourselves while I'm doing some stuff here. We're on. Excellent, brilliant. All right, so do I need to do it again? Okay, all right, but I'll do it from a different part of the room. I'll annoy the camera people. I'll do it from over here, so all the people at the back can see. All right, goes as follows. Arms out front. Right hand over left hand. I'm not lying, it really is my right hand over left hand. All right, then you go palm to palm, right? Wiggle them little fingers, wiggle them thumbs, and when you're ready, just come on back. No. Okay, the answer's just no. Whoa. Do I need to do it again? All right. Okay, I'm getting serious. Take the jacket off this time. All right. Okay, question. Do you want me to actually give it away? Yes. Not yet. All right, not yet. I will half give it away. I'll help you out. I'll give you half a hint. Actually, if I put my teacher's hat on, there's a very good piece of math pedagogy here. I know it's like a gimmick, but it's actually cool and fun and teaches some math thinking. I've given you a problem, and I'm echoing. I've given you a problem, is that right? I've given you a problem for which you know what the answer's meant to be. The final result is that. So what's a very good strategy if you've got a math problem, or any problem in life, and you know what the answer's meant to be? Work backwards. It's so obvious, so straightforward, but people forget to think about it. It is a powerful technique, so let's do it. If this is the answer, let's reverse engineer it. Where must this have come from? Must have come from that. And if you loosen up your fingers, I bet that feels very different from what you were first doing. Does that feel different? Okay, so I've half helped you. We started at the end position, and we got to this funny feeling middle position. Your job now is, can you now start at the beginning and somehow get to that same funny feeling middle position? How's that for half a hint? Okay, is that helping some people? If you're like me, it doesn't help at all, because I'm very slow on these things, really slow. Yes, no, no, yes. All right, how about we do this? Whilst I'm being particularly boring for the next 43 minutes, you can amuse yourself by secretly doing something under the table or something like that. All right? So, but if you want me to give it away, questions at the end, just ask me. I will totally give it away. But cool. That's the International Maths. And by the way, I'm not joking. If you Google it right now, Google International Maths, you will find it. It's out there. People in Tanzania are doing it probably right now as we speak, in Belgrade, in Tokyo, in Sydney, all over the place. All right, let's do what I'm meant to be doing. Where's the clicky thing? Uh-oh. Oh, here it is. Great. Let's talk about a dozen proofs that 1 equals 2, a misguided review of all of mathematics. Let's do it. Are you up for it? Yes. Here goes. All right. I press that button. All right, so this is the one I put in the abstract, because this is a classic one. This actually confused people way back in the 1500s, 1600s by Guadalberto de Monte, who actually thought he had proved the existence of God from this very example. Now, I'm not going to be so bold. I'll prove that 1 equals 2. But here's what he did. Classic result. He said, OK, look at the number. Well, don't look at the number. Look at a number, 0, sorry, 0. OK, 0 is just 0 plus another 0 if you want, plus another 0 if you want, plus another 0 if you want. It could be a whole bunch of zeros. 0 is just 0 plus 0 plus 0 plus 0 plus 0. No worries there. And he said to himself, well, OK, let's get strange. Let's write 0 as 1 take away 1. So it's just 1 take away 1, plus 1 take away 1, plus 1 take away 1, plus 1 take away 1, which after all is just really, where did I point? 1 plus negative 1, plus 1 plus negative 1, plus 1 plus negative 1, plus 1 plus negative 1. Grand. And he said, well, hang on. Think of that as actually 1 plus negative 1 plus 1, 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 and so on. Which is just 1 plus 0 plus 0 plus 0 plus 0 plus 0, which is just 1. So add 1 to both sides, you get 1 equals 2. Woo! All right, so I'm going to convince you a dozen times over that 1 equals 2, but maybe I've just done it right now. What do you think? Do you believe this? No. Okay. Well, what's wrong? All right, okay. I heard the words infinite series, hard for me to hear up here, but yes, this drove mathematicians bonkers in the 1400s, 1500s, 1600s. Apparently, infinite series are kind of weird. All I really did there was rearrange the parentheses, the brackets. I just did the associative law, which is fine in algebra. You always do rearrange the order of operations when you, well, or order of thinking when you do algebra. But apparently doing it on infinite things is, well, troublesome. So people got very nervous about infinite sums. This was causing a bit of a panic in those 1500s, 1600s, especially when calculus came along, there was more panic. So, all right, so you might argue, yes, infinite algebra is actually has to be steered away from. It's a little bit scary. It's much more subtle than first appears. So you might object to that proof. Don't worry. I've got 11 more. I'm going to convince you that 1 equals by the end of this morning. All right, okay, ready for proof number 2 then? If that one's not quite doing it for you, here's this one. I have to do the classic school algebra one. I bet everyone has something similar to what I'm about to do right now in their minds, but I have to do it. It's this. Let x equals 1. People think in an algebra class that x can actually be a number, so I'm going to make my x a 1. In which case, if x is 1, x squared take away x equals x squared take away 1, because x is 1. Yeah? Yeah. Well, seems irresistible since I've been factoring all my life to factor the left-hand side, a common factor of x. So think of that as x times x minus 1. And I've got a difference of 2 squares on the right, x plus 1 times x minus 1. Grand, true, fabulous, nothing wrong with that. Oh, it's a common factor of x minus 1. Cancel them out. Maybe not. There we go. And I've got x equals x plus 1. But what was x in the first place? It was 1. 1 equals 2. Yay? Nay? Okay, some people are nodding, but most people are going nay. Okay, you don't like the cancel. I heard you giggle at the canceling part, is that right? Because actually that line there is actually true. It's saying that 1 times 0 equals 2 times 0. There's actually nothing wrong with that line. It's the actual canceling the x minus 1 part. That's 0. Oops, we can't divide by 0. Causes all sorts of woes. In fact, 0 was also another troublesome entity in the history of humankind's mathematical thinking. People weren't even sure if 0 was a number in the first place. I mean, what does 0 count? Nothing. So is it even a number? And then doing the arithmetic with 0 was really troublesome as well because of this sort of trouble. So we tend to say today, no, don't divide by 0, not valid. All right, okay, well, you shot me down on proofs, 2 proofs so far, but I'm not worried because here's a bonus proof for algebra. Let's solve this quadratic in a very unusual way. X squared plus x plus 1 equals 0. I can tell you right now, x is definitely not 0. 0 is not a solution to that equation. It does not make a true number sense putting x equals 0. So I know x is not 0, in which case I will divide by x because it's not 0. And I'll write it this way. X plus 1 over x equals 0. Now if I just solve for x, I can actually see that x is negative 1 minus 1 over x. Grand. In fact, what I'm going to do, I might as well just, a little pointy thing, I'll take that expression for x and substitute it in right in the middle there. So it'll be x squared plus x plus 1, but I'll write that for x now and get a very scary looking formula. X squared minus x minus 1 over x plus 1 equals 0. But when I do that, negative 1 and plus 1 cancel. So this really is just x squared equals 1 over x. Multiply both sides by x, I get x cubed equals 1. A number whose cube is 1? Oh, x is 1. Brilliant, x is 1. So let's put it back into the formula. It tells you that 1 squared plus 1 equals 0, in which case, 1 squared plus 1 is 0, 3 equals 0, divide by 3, get 1 equals 0, add 1 to both sides, gets 2 equals 1. Done. Cool. Yay or nay? Nay? What's wrong with this one? Oh, you're telling me that you realize this x cubed equals 1 actually has 3 different solutions. I just happened to choose the third one, which turns out to be incorrect. Because it turns out the other 2 are complex solutions, the complex roots of unity, and in which case those 2 turn out to be the actual solutions that begin in quadratic. I increased my solution space in my little bit of algebra there and happened to choose the wrong final solution, well, a supposed solution. All right, you shot me down, but I fear not. I've got many more proofs. We're golden. Okay, let's go down a bit. Let's do a proof by fractions. Let's go to elementary levels. All right, there's a very little known fact about working with fractions in base 10. I don't know why this is not out there, but it's okay to just cancel 3, 6s, and 9s in base 10 fractions. What do I mean by that? So here's some fractions like 65 26ths, and 16 64ths, and 49 98ths, and so forth. Well, that first one, 65, 26, I see, where's my point of this one? It's really 5 times 13 and 2 times 13. So actually, that's really 5 tooths. I just like cancel out the 6s, literally, and get 5 tooths. 16 64s, cancel out the 6s, really is 1/4. 49 98ths, cancel out those 9s, really is 4/8, 1/2, and so on. You can do double digits. 163 over 26, cancel out those 3s and 6s, really is 1/2. I kid you not. 266 over 665, cancel those 6s, really is 2/5. Fabulous. It's really handy. Love base 10 because of this. Oh, in which case, I'll use my advantage. So 13 32ths must be the same as 1/2. Just cancel out those 3s. In which case, arithmetic says just do a little cross multiplying or something. 26 is 32, subtract 26 on both sides, divide by 6, add 1 to both sides. 1 equals 2. All right, what do you think? Well, you're saying no. Why? You just can't do what I'm doing? You don't like that? What I love about this, of course you can't do that, because I just happen to select examples where all that is just true by pure coincidence. Pure coincidence. In fact, a really good exercise, can you find other examples which just by pure luck happen to work out? That's a really tough exercise, actually. Then you'll really know your stuff if you do that. In fact, I did share this with some students when I was in my high school days, and one student came back to me the next day saying her father was so obsessed by this, and he came up with this example overnight, which is just incredible. He went beyond 3 6s and 9s, but he found the fraction 1, 2, 3, 4, 5, 6, 7, 9 over 9, 8, 7, 6, 5, 4, 3, 2, cancel all the common digits, really is 1/8. Really is. Wow. All right, so that was just coincidence. No, you cannot just cancel 3 6s and 9s and base 10. Done. All right, well, let's go to complex numbers then. All right, so I is defined as a number with a probability that I squared is -1. Grand. So I'm going to use that to my advantage now. Here goes. 1 is I squared plus 3 over 2. Am I right? -1 plus 3 on the top over 2 is 2 over 2 is 1. Great. So let me just tease that apart ever so slowly. So I squared is really just I times I. And I is really just the square root of -1. So it's the square root of -1 times the square root of -1 plus 3 all over 2. But then I see a product of square roots. Grand. So I'll use that to my advantage. Yep. Oh, within the vinculum and the radix, I see -1 to -1, which is +1. Square root of 1 is 1. A one-line proof that 1 equals 2. So what do you think? Oh, I've got a believer. Excellent. Yes, 1 equals 2, we're done. Fine, I can stop now. Actually, this is subtle. What's really going on here? Yeah, I like walking around. I'm going to come over here. This is really dangerous. You often see textbooks don't define I quite this way. They say I is the square root of -1. But the danger is this hook symbol, this radix symbol, is actually a symbol from geometry, where it really was the root feature of a square. What is the root feature of a square of a given area? In which case, you're speaking geometry, you're speaking only positive areas and positive lengths. It means the positive root. So when I start doing this sort of thing, what's the root feature of a square of -1? Technically, the notation means nothing. But we know arithmetically we want to start playing with that, in which case, when people define I to be the square root of -1, there's the danger. There's actually 2 square roots of -1, I and -I, plus or minus. And I've just really messed with our minds here. When am I going plus or minus? So the proof here should be, I agree with 1 equals that, I agree with that. I get a little bit nervous right there, because technically, square root of -1 should be plus or minus. That should be a plus or minus. So I've got plus or minuses all the way through here. I've got some ambiguity from this point onwards. So I guess I've really only proven that 1 equals plus or minus 1 plus 3 over 2. And I need to choose the -1. So there's ambiguity in my pluses and minuses. I'm being very uncareful with them. All right, yeah, even I broke down my proof. I don't like that one. Okay, move on. All right, next proof. We can do it. Let's go very elementary. Let's prove by coloring. So here's a square. Here's a square. I'm going to color it. In fact, first I'll just color the bottom edge, and that uses some paint. Would you agree? Yeah. Or if I decide to color the whole square, that uses a lot of paint. That uses more paint. With me on that one? Now I will tell you the size of that square. It's 1/2 meter by 1/2 meter. All right. So how much paint did I use on the left? Well, it's just the bottom edge, which is half a meter long, so I used half a unit of paint. On the right, I used the whole area, which is half times half, a quarter of a unit of paint. Clearly, the left side is less paint than the right side, so it must be the case that a half is less than a quarter. In which case, do some arithmetic, half is less than a quarter, therefore multiply 4, 2 is less than 1. We all know that 1 is less than 2, so the only thing left over is to conclude that 1 and 2 are the same thing. Yay or nay? Yay, okay, that's it, done. The danger of not understanding units properly, is that the problem? Okay, okay. Units, that's why we don't do science. Units are really hard. All right, okay, proof by geometry. Proof by geometry. All right, let's do it. A classic, geometry proof. Here goes. The diagonal of the unit square, which caused so much woe in the history of humankind with Pythagoras and all the rest. What is the length d? What's the length of the diagonal of a square? Square root 2. Good old Pythagorean theorem tells me it's root 2. Grand, about 1.414. Super. All right, but let me get to that diagonal in a different way. So let me approximate the diagonal with a little zigzag staircase. All right, so I've got 3 pictures on the left. I've got one little zigzaggy thing going on here, very broad, but I do a finer staircase, or even finer staircase. You can see that wants to become the diagonal, correct? All right, question. How long are the horizontal red sections on the leftmost picture? 1. So you just swoop them down and see it's the same length as the base of the square. And how long are the blue vertical sections of that picture? Match the side length there, so 1. So what's the length of that staircase? 2. What's the length of this staircase? 2. Same thing. What's the length of this staircase? What's the length of every approximation to the diagonal? 2. It's 2, 2, 2, 2, 2, 2, 2. So what must the limit be? If it's all 2s, the limit must be 2. Grand. Oh, so the square root of 2 equals 2. Yep. So some arithmetic, square root of 2 is 2, square both sides 2 equals 4, divided by 2, 1 equals 2. Same fellow believes me again. Excellent. What's going on in this one, like really? What's really going on? Okay, so I heard convergence, interchanging limits is dangerous or something like that. Okay, this is another thing that drove folks batty in the 1600s, 1700s, and even 1800s. What is this thing called calculus where we do all these limits? Because paradoxical things were starting to emerge. What does continuity actually mean? What does convergence mean? It turns out, yes, this is a very subtle issue. There's no doubt that the diagonal is converging pointwise to the true diagonal of the square. My staircases are converging pointwise to the diagonal of the square, which makes no claim about what's going on about arc length. Turns out arc length need not converge, even though the function is converging itself. We have all these different notions of convergence, and it turns out you have to be extraordinarily subtle because weird things can happen like this. 1800s, those guys, Cauchy and Weierstrass and all the rest, were really trying to pin down what is going on, because these examples like these are telling me something subtle is afoot. And it took a long time for folks to figure out what's really going on there. All right, well, geometry's hard. Let's move on. Proof by rearranging. All right, here's another little classic proof. So I'll take that one. Let's take the infinite sum, the alternating harmonic series. You can kind of see on a number line, it does want to settle down somewhere. It turns out it converges to log 2, which is about 0.69. Great. But let's play with it. It has some value. So let's call x, which is about 0.69. And what I'm going to do is take that value and double it. So 2x would be double everything. It would be 2 minus 1 plus 2/3, take a half, plus 2/5, take away 2/6, which is a third, plus 2/7, take away 2/8, which is a quarter, and so on. But stare at it. It's kind of cool. Stare at it. So, do you see right there 2 minus 1, which is 1? The answer is yes, you do see it. Yep. You see a negative half there. There's a negative half. You see a 2/3 take away 1/3, which is a third. You see a negative quarter over there. There it is. You see a 2/5 take away 1/5, which is a positive fifth, and so on. In fact, you can see if you just rearrange this thing, it really is the original sequence. 2x equals x, and x is not 0. Therefore, 2 is 1. Yes? No? Yeah. All right. It's this whole convergence of infinite sums again. Same thing back in the 1500s. This sort of thing drives people batty. So yes, the early proof, the very first proof, is about just the associative law. It works fine for finite sums, seems to be troublesome for infinite sums. This time I'm actually moving things around doing the commutative law. Seems that that's also troublesome for infinite sums. Fine for finite sums, move things around as much as you like. Infinite sums, all bets apparently are off. Infinite series is scary. That's the message of this one. All right, all right. I'm not worried. That was 7 proofs. I got 5 more to go and plenty of time. All right, here goes. Here goes. Proof by experiment. If I can't do it mathematically, I'm going to do it by pure experiment. All right, right here, I have 2 wheels. Hopefully you see arrows pointing upwards. Yes? All right. What I'm going to do is I'm going to rotate those wheels until those arrows are pointing upwards again. So I'm not doing a very good job. Whoop, 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 whoop. Have I done it? Okay. Okay, so those wheels had to roll around, what, the full circumference before the arrows were aligned and pointing upwards again, is that right? So that was a full circumference around each other. All right, but now watch this. I'm going to keep this wheel fixed and just roll this other wheel around it. Oops. I'm trying to be real, I'm trying to not cheat. Are they aligned, pointing upwards? Going round half the circumference is exactly the same as going round the full circumference. Half equals 1, double it, 1 equals 2. Yes? Whoa. What do you think? Okay, we've got more believers. Yes. 1 equals 2, half equals 1, same thing. All right. Do you want me to let you into what's really going on? This is the effect of compound motions. I'm just messing with our minds. If I go back to what I first did, just roll the 2 wheels together. Notice if I go around half the circumference, you do see the arrows aligned, but pointing downwards. I want them pointing upwards, so I could then just take the system and then rotate the whole system like that. Now, or I could do the following. I could actually do what I was doing, go halfway around, and do that rotation at the same time. That would have the effect of keeping this wheel fixed. So what I'm really doing is just go halfway around. The arrows are technically pointing downwards, but I've rotated the whole system at the same time upside down. So I've given the illusion that I've just actually, well, I've done something funny, but I haven't. Compound motions are very hard to decompose, is my point. Okay, all right, okay, so you got me on that one. All right, but then let's try this one. Let's try this one. Let's do another experiment. Proof by rotation. If this is kind of an anti-proof, I'm going to prove that 1 is different from 2. Which seems the complete opposite of what I'm doing in my talk. So imagine, okay, it's a very classic trick. So imagine like I'm a waiter with a tray of food or something here, and I've got my feet planted on the ground. I'm going to give this tray of food 1 full rotation. And you see me do it. Can you imagine what I'm doing? Is that 1 full rotation? Yes. And look how contorted I am as a result of doing 1 full turn. So 1 full turn has put me in a very tricky position. All right. Now, do you believe I can give that tray of food a 2nd full rotation in the same direction whilst keeping my feet firmly planted on the ground? No? Ow, ow, ow. Ooh. Whoa. Whoa. Yeah? 1 full turn, 2nd full turn. Was that really 2 full rotations in the same direction? And look at this, my arm is back to being untangled, I'm back to the identity state. So actually doing 1 full turn is fundamentally different from doing 2 full turns. With me? But try it, it's kind of cool. So take your glass of orange juice. I dare you to bounce on your hand. All right, well just do it without anything. Just get the feel for it. It's kind of funky, kind of cool. Woo! Yeah, if you want it to be really cool, do it with both hands at the same time. Yeah, yeah. By the way, traditional folk dance in Thailand is the candle dance. Dancers will actually do this sort of motion with candles balanced in their hand. They're actually doing this. But here's my real point. So I just showed you that 1 full rotation is actually fundamentally different from 2 full rotations. The 1 is not 2. However, I did actually just show then doing 2 full rotations is actually equivalent to doing no rotation at all. I'm back to the identity state. So actually, I've just demonstrated that 2 equals 0. Ah, in which case, oh, watch, you did watch me. 2 equals 0, divide both sides by 2, add 1 to both sides, 2 does equal 1 after all. What do you think? You can't argue that one. So what I've done here is the famous Dirac string teacup trick. I can't remember what Waiter's trick, I think he called it. I mean, if you've ever studied quantum mechanics, everything comes in small quantized packets, except for angular momentum. It comes in half packets, which is weird, because Dirac actually realized in our physical universe, it actually requires 2 full rotations to get you back to the identity state. So it's like 2 full rotations is the fundamental unit, not 1 rotation. It's only half a unit. So in quantum mechanics, angular momentum is often given half packets because of this, our physicality of the universe. So here's my advice. If you're ever on a dance floor and you twirl around an odd number of times, just do 1 extra twirl to get you back in the same quantum state you started with, okay? All right, here goes. Proof by rotation. Okay, I'm not worried, 9 down, but I've got 3 more to go. I'm going to convince you. It's going to happen. All right, proof by area. Let's go back to like coloring books. Very simple idea. I'll draw a rectangle, maybe, yes. And I'll draw the diagonal rectangle. So there's a rectangle. It's actually, a rectangle is divided into 4 parts, and that one diagonal chops each purple rectangle in half and chops the whole thing in half, which is great. There it is. In which case, I would argue, since the top half of the diagonal matches the lower half of the diagonal, and each purple split in half, those 2 yellow regions are equal in area, just by pure geometric thinking. Great. We'll actually work out the areas. You'll see that one is actually a 2 by 8 rectangle, and the other one is a 3 by 5 rectangle. Oh, 16 equals 15. Subtract 14 equals 1. And you can actually draw this, and you can actually see it for yourself, and you can cut it out. You can do whatever you want with it. You will see that 2 equals 1 from that picture. Yay or nay? Don't like that one? What's going on? Okay, I'll use the Fibonacci numbers, true. There's a very classic, lots of different variations of this. You're right, I'm just being a bad drawer. Have you noticed my lines are very thick? And when you try to draw these hands, you don't actually notice that little error. It actually does miss that little point there, but it's so close the human eye usually can't tell. If you're doing thick markers and thick scissors, you cannot tell, so it looks like it's real. But no, if you actually work out the slopes or something like that, you realize the slope in the purple, each of the purple rectangles is not matching. Close, but no cigar. All right, okay, fair enough. All right, okay, I'm still not worried. I've got 2 more to go. We'll be good, we'll be good. Okay, proof by pure thought. So if I fail with like geometry and practical things and experiments, and I fail with like basic algebra and infinite series and all the rest, pure thought. Here goes. This one is very abstract. It's a bit brain-hurty, but let's go for it. I'm going to ask, what is the largest counting number? Okay, strange question. Okay, answer. 1 is the largest counting number. Here's why. So, we'll show that no other number can be the largest counting number. Which would then say, oh, the only possibility for the largest counting number is 1. So any number that's not 1, I claim, cannot be the largest counting number, and it goes as follows. Suppose I have a number that is, in fact, bigger than 1, n is bigger than 1. Then clearly, if I square both sides, n squared is bigger than n. Sorry, multiply both sides by n, sorry. In which case, oh, n squared is bigger than n. I was wrong. N cannot be the largest counting number. Any number that's not 1 cannot be the largest counting number. Therefore, 1 is the largest counting number. In which case, 1 is bigger than 2. And we all know that 1 is smaller than 2, in which case 1 must be equal to 2. Yes? Awesome, thank you, awesome. Yay or nay? What's really going on here? Yeah, this is actually very subtle. Something going on here. What did I do? What's perturbing you? That's right. The premise of the whole setup seems to be perturbing. Because I said here, what is the largest counting number, assuming there was 1 in the first place. So actually, everything I did there is correct. Under the assumption there is a largest counting number, that counting number is not 1. Well, the thing is, I don't think it's the largest counting number in the first place. Everything I do is moot. All right, but here's actually, I love this because it actually illustrates the danger of the premise of the question. Here's a very classic example. So believing that answers exist is delightfully, fabulously quirky. Classic one. What's 0.999999 forever? Eins, uno. Okay. Here's the classic example you see of how people demonstrate this using algebraic techniques. Give it a name. Call it Xavier or something. Everyone seems to be obsessed with X. So 0.999 is Xavier. what could you do to Xavier right now? Multiply both sides by 10, in which case 9.9999 would be 10 Xaviers, yes? Okay. Then what's the next classic thing we tend to do? Subtract, in which case 9.9999 forever, take away 0.9999 forever is just 9, would have to equal, oh no, I didn't subtract. Oh, no, I didn't subtract. Actually, do you see what I did? I just separated. Sorry, most people subtract. I decided to do something different. I forgot. Yeah, because this 9.999 forever is really a 9 plus Xavier. There's Xavier, the 0.99. So 9 plus Xavier is 10 Xaviers, which is equivalent to subtracting, because that tells me that 9 is 9 Xaviers, in which case Xavier is 1. Yep. Voila, we're golden. 0.9999 forever is 1. Do you like that? Yeah, I like it too. All right, so, but here's my thing. Everyone seems to be obsessed with infinitely many 9s to the right of the decimal point. Has anyone ever considered infinitely many 9s to the left of the decimal point? In which case, I'm going to repeat that exact same algebra, because if you believe it there, you're going to have to believe me here. You can't just pick and choose when you want to believe stuff, if you're committed to that. So let's do it. Step 1, give it a name. Let's call it Yvette. Let's multiply by 10. Can you see what you're going to get if you multiply by 10? Right, just add a 0, which means, I guess, keeps the number same. Now put a 0 at the end. So a whole bunch of 9s ending in 9 is Yvette. Whole bunch of 9s ending in a 0 is 10 Yvettes. All right, I could subtract, or I could do my clever thinking I did before. How does that translate to? Do you see that left-hand side is all of Yvette, but it's missing a 9? So the left-hand side is actually Yvette minus 9 is 10 Yvettes. Is that right? Can you see that? Or we can subtract, it's fine. In which case, oh, so negative 9 is 9 Yvettes. Yvette must be negative 1, and voila, whoops, and voila, that number is negative 1. In fact, let's get worse. Let's have infinitely 9s to the left and to the right of the decimal point. Yeah? In fact, let's do it. Let's do it. Same thing. Give it a name. What name is it going to be? James. It should be James, but I can't get any name. Whoop. Call it Walter or something. Multiply by 10. What do you get? Am I right? Just shift the decimal point, but it turns out being the same number. So 10 Walters is the same as 1 Walter, in which case Walter is 0. So infinitely 9s to the left, infinitely 9s to the right is 0, which actually is beautifully consistent, because you just told me 0.999 forever to the right is 1, 0.999 forever to the left is negative 1, negative 1 and 1 together gives you 0. Whoa. So, do you choose to believe the algebra? Because apparently, that middle one says, if I get at my calculator and I go 9, and then go plus 90, plus 900, plus 9,000, plus 90,000, I'll get all the 9s. In the end of time, I will see negative 1 calculator. No? Then what's going on here? All right, so what's really going on here is, do we believe the premise of the question? Everything I've got on the board right there is actually absolutely solid and correct. I cannot argue with any of that, if I'm very clear on what it's proving. The first one, the left one, says, if you believe 0.999 has a value, then that value is 1. Whether you believe it does have a value in the first place, I don't know, it's up to you. If you believe a bunch of infinitely many 9s going off to the left has a value, then we prove that value has to be negative 1. Now, it's up to you to believe if that's meaningful to you or not. And voila for the third one. All we've proved on the board right now is if you believe this has a value, here's what the value has to be. It's up to you to decide if you want to believe it has a value in the first place. Seriously, it is up to you. So now, what's the standard belief in most calculus courses and below? What do we like to say about that one? Do we like to believe that has an answer? In which case, yeah, it's 1. What do we think about that one? Do we like to believe that has an answer? In which case, all that's moot. Who cares? If you believe it has an answer, the answer is negative 1. But you don't believe it has an answer, so we're good. By the way, you can create arithmetic systems for which this quantity is absolutely meaningful. It's the 10-adic system. And guess what value it has in the 10-adic system? Has to, because we just proved if you think it has a value, that value has to be negative 1. In fact, How do you represent -1 in computer science with those little, binary things going on with those electric chips that are either on or off? How's the number -1 represented in computers? Yeah, it's actually, well, the base 2 version of 9999 off to the left is 11111 off to the left. So they only go for, 16 bits or something like that, how many bits they are. They do as much as they can, but they actually represent -1 this way because it actually is the correct thing to do. Actually, in which case, as a close approximation, -1 is grand. All right, okay, so you shot me down on all the proofs I have so far, but I genuinely believe I'm going to convince you that 1 equals 2. I have the final proof right now that's truly, really going to do it for you. Are you ready for proof number 12 that's going to absolutely convince you that 1 really is 2 no matter what? The answer has to be yes. Okay. And if you want, then I'll get the math salute away. All right, here goes. Proof number 12, the one that's really going to do the trick. Proof by shopping. Goes as follows. I'll be silent on this one. I'll let you just take it in. I mean, what can I say? What can I say? Whoa, whoa. So, I'll stop there. But I do want to check. How's this? So, to celebrate the joy of mathematics across the globe and all the incredible work you guys do, let's salute mathematics with the International Math Salute one more time. Are you ready for it? Yes, I am watching. You've had 40 minutes to practice. Arms out front. Right hand over left hand. Palm to palm. Wiggle them little fingers. Wiggle them thumbs. Wiggle them little fingers one more time. And when you're ready, wait for it, wait for it, wait for it. When you're ready, come on back. Ah, good job, guys. Well done. Excellent.
Got this certificate.
Well, thank you. How do you want to do this? Oh, yeah, okay. My stuff. Where am I sitting down? Oh, so much. Real quick. Okay. Do you actually want me to give it away, that math salute? Okay, I'm going to give it away. So I've got 2 minutes. All right, I'm going to give it away. If you don't want to know the answer, just like go wow, 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 or something. All right, I'll do it very slowly. The idea is this. Arms out front, and obviously I'm not doing what most people do, which is twirl their thumbs in opposite directions. It feels very natural for us humans to do, and I'm not doing that. What I'm doing is the equivalent of, imagine holding a big rubber red ball. It has to be red. And what I'm doing is just turning the ball upside down, essentially, and then your hands are ready to just come on back. Except I have to do that with my wrists touching. So here's how it goes. So, arms out front, right over left. I get the top hand, the right hand. We'll do it one hand at a time. Thumb just goes down, no tricks. No tricks with the top hand. All the tricks are with the bottom hand, the left hand. Your thumb is currently up. It will turn 180 degrees and go downwards, but turn the direction feels completely wrong and unnatural. Thumb towards the palm. Have your thumb touch the palm. Scrape down the palm. Ow, ow, ow. It's so wrong. Wiggle, wiggle, wiggle. Come on back. Wow. All right. Now you know the secret is beholden upon you to go back to your home communities, practice this 20 times tonight in your room, so you're as smooth as I am, and then share it with back your home communities. Is that a deal? Good deal. Thank you.
Thank you, James. Wonderful. I invite, we have a couple of few final announcements before we break. I invite Bill Stinkin, Foundation member and Investment Board Chair, to the stage. We will now have the foundation drawing. There are 3 prizes. that will be drawn from the spinning red cylinder behind me. The first award will be the complimentary registration in Spokane 2020, or a 3-year AMATIC membership. Mark Early, Columbus State Community College. And for the 2-year AMATIC membership, from Pima College, Pima CC, Jose Maria Menendez. And finally, for the 1-year membership, Chucky Hairston, retired. We will be in contact with the winners. Thank you, Bill. So I have a couple announcements. AMATIC is accepting proposals for the 2020 conference in Spokane from now until February 1st, 2020. I hope that we will see you in Spokane next year. Visit our new My AMATIC member site, log in, join some communities, and engage with your colleagues. There it is. Visit our exhibitors in the exhibiting hall immediately after this session. In the recent election, the following individuals were elected to the 2020-2021 AMATIC board. Will the incoming board members please stand up and be recognized? Thank you. I ask the incoming board to come up near the stage after this session. This concludes the 2019 Saturday General Session. I invite you now to visit our exhibitors and enjoy the rest of the conference. Thank you.